Well, thank you all for coming out. I know it's a busy time for everyone, not just for schools. A lot of people are off campus and everything else. And got a pretty good crowd here, I thought, for people coming out to hear what I have to say. But a lot of this, I'm going to say, some of you are familiar with some of the message, and then, but I do encourage you to interrupt me, ask me questions, challenge what I'm saying, and so on. And if there's anything that is incomprehensible, my slides are available on my website. So if you missed something or want to go through it again, when the video is ready, I'll post that as well. So that way you can hear me again, hear my voice again without me actually being there, which is might even be better. I'm not sure. So the basic the abstract was sent out. So as a prelude, I'm going to just introduce this just as a form of terminology. There are two main schools of probability or statistics. One is what we call frequentist statistics. The other one, which is often called Bayesian. And so I'll use those terms in this talk. They go sometimes by other names. They differ fundamentally on their definition of probability, and you wouldn't necessarily think that these two different definitions would lead to any practical differences, but it does actually end up being somewhat different. So the frequentist defines probability as kind of a long-run relative frequency. So essentially, the reason that a coin is 50-50 is because if you were to flip it many times, identically that you would come up heads 50% of the time. And so in some ways, the probabilities are intrinsic to the experiment or intrinsic to the object. And it only applies. This definition only applies to those things that could reasonably be repeated many times. The Bayesian definition essentially says probability is just a number we ascribe to our state of belief of a claim. And sometimes it goes by the name of conditional probability, because you're always having a probability of something given my information, so it's conditional on that information. In this case, because it's really a measure of our knowledge, of our state of knowledge of the system, the probability of a coin being 50-50 is given because we lack any other detailed information about the coin flipping process, and the coin itself has a symmetry to it that then gives rise to assigning basically complete ignorance to the different possibilities, heads and tails, and that gives you 50-50. So those are the two main schools, and I'm gonna here's the outline of my talk. I'm going to kind of tell you what the problem is I see it. I'm going to describe what Bayesian inference is and some of the disagreements and the agreements. I'm actually going to focus more on this in this case, and then kind of why there's some disconnect between kind of what I consider to be the success stories in the field and what we actually teach students at the intro level. So here's the problem as I see it. Here's a sampling of what I consider to be many of the recent successes in statistical inference. You have people like Sebastian Thrun, a probabilistic robotics. He won the DARPA challenge for the automatic driving car. You have Nate Silver, who got famous in predicting elections for presidential elections and state elections and so on. You have all these people, Andrew Ng works for Google, and so on. Every single one of these cases that you look at as kind of being successful, they're all Bayesian. Every single one of them. And then, if you look at intro stats text, so this is the kind of stats 101, or 201 here, but like the first stats class that you would take. And here's a range. I know that the Man book on the left and the Nvidia Monk book both have been used here at one time or another, and there are other ones. The other Nvidia book down there is a bit more advanced, but again, is an intro stats book. You look at all these. I'm just going to do an example. Every single one of them is frequentist. So the problem as I see it is that when you look at the successes in the real world right now on real application, every single one of them is Bayesian. and then you look at every single textbook from the intro level, and it's all the other schools. To me, that disconnect by itself, regardless of the history or anything else, should tell us something. And why is there this big difference, and what should we do about it? Is another thing. Tom, I wanted to, you came a little late, but I wanted to open up to anyone. If you can interrupt, you can ask questions. Please do challenge me on anything along the way. So
I answer a question.
Sure.
No, that's a very, very simple one. So a lot of the books have three approaches. They say classical, frequentist, and subjective.
Classical is frequentist.
As I was asking you, so you're saying
that I don't think there is any difference, right? And so
well, they give
sometimes it's called orthodox too.
Well, they give examples of differences.
Yeah, I don't think I've ever heard of a distinction between classical and frequentist.
Well, there's an example in one of the books might be something where if you have you're producing cars, and so based on the frequency, like 10 out of 500 of the cars produced at this manufacturing plant,
right,
lemons. What's probably the next car is going to be a lemon. That would be considered frequentist as opposed to classical. If you went to look at the original 500 cars, and 10 of the 500 were, say, lemons, and you randomly select one of the cars. So one's the next one coming off the assembly line.
Oh, okay, yeah, right.
So there's a fine distinction. But
interesting. Okay, I wouldn't have made that distinction, and I think in their probability, I think in terms of the interpretation of probability, they end up being the same, or one of them is essentially a Bayesian calculation, and the other one may not be. But I do know that the term subjective probability is always what they're referring to Bayesian. So that's that way. So that's
that wasn't the question. Subjective is the Bayesian, just the difference between frequentist and
right. I've never heard that difference really.
Yeah. A lot of the books they'll do three approaches too.
Really? Yeah, it's funny. I've not seen it that way. So okay. Yeah.
Are you going to talk about the evidence for the claim that Bayesian is more successful?
Okay. I mean, I will comment on it. All right, but already, I would say just empirically, if all the major players in the field are all Bayesians, to me that immediately answers that question. Without me saying anything. It's like if you don't build the automatic driving car with frequentist statistics, you use the Bayesian approach. That immediately tells me something. So. Maybe that can tell different people different things. So, but I kind of see that there. Now, what I did, this is what I often, when I first look at this is the pattern that I would see. You'd see Bayes' rule or Bayesian statistics often mentioned in the intro of stats class, and it usually is somewhere in like chapter 2 on probability, and they do like 2 examples. And then it's chapter like 14 star, the kind of the optional advanced chapter on Bayesian statistics, and that you never end up getting to anyway. So that was the thing. So when I grab this is just a section from their index, and you can see that kind of Bayes stuff appears on page like 80, and then again at 400, something like that. So it has that kind of structure to it. And when I was making these slides, I was going to show that for several of the textbooks. And it even surprised me when I open up Man and Bayes is not even mentioned in the index. And then I look at Navidi and Monk and it's not mentioned there either. And which is really remarkable. Because even if you don't think that it is the approach you're going to take, not even mentioning it to me is pretty remarkable.
Do any of the Bayesian, sorry, I came up to that right now.
Yeah, that's what. So now we say, okay, well, what's kind of the Bayesian? So you go to the library, you find Introduction to Bayesian Statistics, and it's great. I could take this book off the shelf, give it to our freshmen, and so on, and you get pages that look like this, which I think you could imagine a freshman not quite getting this. Would you agree?
Yeah.
Okay. Yeah, it's like. Yeah. So completely obtuse. And look, another one. all set theory and everything else, and
Really accessible.
right, exactly. It might be an introduction to someone who has advanced math, and I think, and I might be wrong because I didn't get a math PhD, got a physics PhD, but I would imagine these books are often introductions to Bayesian statistics for graduate students, like kind of going in, and maybe you can confirm that or not, but this is the way that I would see it. Then there's this one, which actually is an intro stats book at about the level that we're talking about, and you can get this on Amazon for $200. It's a thin paperback, and it comes with a floppy. So you can see kind of a problem there, and that's actually the most recent edition. And the only other one that I was able to find is Think Bayes by Alan Downey, who John and Alan and I went up to Olin College last week, and he wrote this. And it's actually a very nice book for many things. It wouldn't fit well, I think, with our students. It basically is everything in terms of programming, which is an interesting approach. So all of it's numerical. He doesn't do any of the kind of calculus. Everything is programming. However, I think because he's teaching at an engineering school, so programming is really a core part of their freshman curriculum. It fits very well there. Doesn't fit well, I think, in other cases. So that's my thing. But that's it. So there isn't one otherwise. So let me talk a little bit about kind of what Bayesian statistical inference is for those of you who may not know. Kind of, and I'm going to actually start with the wrong definition. This is coming from Frequentist stats books that it has. So we have this is the expression of probability that I said before for the Frequentist is the proportion of times that some event A would occur in the long run where the experiment would be repeated over and over and over again. I can demonstrate empirically that this is the wrong definition of probability. And I'll show, and with a single picture, and I'll show you that picture later. The other, when they talk about subjective probability or Bayesian probability, they often say things like subjective probability is assigned arbitrarily. That's just factually wrong. And so these sorts of kind of, I think, misunderstandings of the Bayesian approach, I think, underlie some of the reasons why there's this disconnect that goes through. But let me show you the reason why I think. Yes?
At the same time, no math books that actually introduces probability formally would use this definition anyway.
Right. Yeah. Well, certainly. Right. I mean, well, I think it's trying to be complete, or I mean, I think first year students are not at the level where they can really distinguish between these different definitions. Right. Clearly that's not a point. And any textbook that kind of starts raising that distinction a lot is that's not gonna work. All right. That's why I bring it up here because you guys are not first year students, and so that's the thing.
No. But it's just I know this kind of definition is a didactic tool. You're dealing with math potentially half of the class is math programming anyway.
Right. Yeah. Well,
and
you have that
want
problem.
to keep it
Right.
as simple as possible.
Right. And but you've seen that definition in a lot of intro stats books, right? Yes. It's kind of a classic.
Yeah.
Right. So this whole idea of kind of repetitive experiments can be shown to be, as a definition of probability, can be shown to be false with a single picture, and that's this one. And this is Diaconis. He's a statistician at Stanford who made a coin flipping machine. And this machine flips a coin very vigorously, so it actually spins very rapidly, falls on a pillow, and he's able to get heads 100% of the time on repeated experiments. Why? Because the machine itself has such a fine tolerance for how much energy it imparts on the coin that it gives the same exact flip every single time. So this is truly identical flips. And guess what? Identical flips give you identical answers. Not it gives you 1 and 0, not 0.5, 0.5. And so the long run relative frequency just cannot be correct. And what's the difference is that the reason why we assign 50-50 is that when we have a person flipping it, or if it bounces or whatever, that suddenly our knowledge of the system is such that we have no knowledge at all of what's going to happen, and equivalent states of knowledge have to yield equivalent probability assignments.
Well, isn't that just, that doesn't really disprove frequency. That just says if you flip a coin with that machine, you'll get heads 100% of the time.
Right, but the
So
thing
that
is,
would be my result as I got bigger.
right. Well,
So heads is the probability of a head in that case using that machine and a balanced coin. The probability is 1 that you
Okay.
get a head.
right. But if you so in that case, the probability itself depends on the experiment in many ways.
Well, absolutely.
Right.
You're flipping it the same way.
Now the other way to demonstrate that it is incorrect, or perhaps just less useful, is that if I should have brought a coin here, but I don't have it. I actually have a two-head quarter, but that's another thing. I'll pull that trick on you guys. But if I flip a coin and you assign a 50-50 probability, but I get to look at the coin, right? Just changing my state of knowledge changes the probability assignment for me, but doesn't for you. And that's a sort of thing that again, you can talk about the probability of a single event, and you don't need to have recourse to this kind of long-run relative frequency. The other thing that you can imagine, and I come from a physics background, and so when you start talking about things about like estimating the mass of Saturn, and then you have some sort of distribution on that, it makes sense to a physicist that that distribution is a distribution of your state of knowledge. It's kind of measuring your uncertainty in the experiment. Frequentists would have to imagine like multiple universes in which everything's the same except for the mass of Saturn and the various things, and that starts to, for a physicist, that's like, okay, you're just imagining stuff, and it actually turns out that, just in terms of some of the practical differences, some of the frequentist tests do depend on what you happen to imagine is different. But I'm not going to focus on that. I will actually list a few things. The correct definition, and again, and there are reasons why I'm saying correct, is the Bayesian one, where essentially we have the probability is a measure of our state of knowledge. And then you have things like it has to be consistent with deductive logic and so on. Yes.
I do want to object to that mathematically. I mean, like,
Good.
I'm as a mathematician,
Yes.
if I'm doing probability theory based on the Kolmogorov axioms,
Right.
I don't care anything about this definition or the other definition. I mean, for me, probability is a mathematical...
Well, absolutely. Right. If you're doing probability, great. You're doing a Bayesian calculation. There is no difference between the Bayesian approach and doing a probabilistic calculation.
Yeah, but I mean, I'm just saying, as a mathematician, I have a mathematical theory, axiomatic theory.
Mm-hmm. Yes.
And at the mathematical level, I'm quite frankly don't give a damn about whether you interpret that in a frequentist way or interpret that in a Bayesian way. The math is going to be the math.
Well, that's true. And then you get into some of the practical issues in terms of the types of where the interpretation of probability can come in certain, there are certain practical ways and certain pedagogical ways. One way is, for a Bayesian, you can talk about the probability of a hypothesis being true. Right? A frequentist can't do that. Because by definition, if a hypothesis is either true or not, it doesn't have a long-run relative frequency. In which case, what you have to do is you have to come up with some kind of statistic that then is a function of your data and then has a distribution and so on, in order to get around the idea of having the probability of a hypothesis being true. So in some ways, just in terms of, even if they might come to the same answer, I think the kind of Bayesian description is a little bit more direct and fits with, in many ways, what your natural intuitions are. The other thing is, if you're always dealing with kind of populations, samples and populations, depending on what you imagine your population to be, you can get a different answer. That was the problem that I found where the definition has practical consequences, where they don't agree, and that's where I'm not going to focus on that in this particular talk, because I want to kind of show where they're kind of the same in some ways, and so on. But these are actually the axioms, mathematical axioms for the for Bayesian probability, and you can demonstrate that if you define probability in this way and make sure that it's consistent with deductive logic, and make sure that all equivalent states of knowledge give you the same answer and the same probability assignments, you derive the rule rules of probability, the standard rules that we see, the sum rule, the product rule, the Bayes rule, et cetera, et cetera. I mean, this is the kind of the math that you don't have any question about. And it makes sense. And so essentially all Bayesian inference is applying probability to all statistical inference. That's all it is. There's a kind of a funny caveat to that, not caveat, but kind of a consequence of this, is that any process of inference either agrees with the Bayesian one, or it violates one of those statements up there. It's either not consistent with deductive logic, or if a conclusion can be reasoned in more than one way, it gives you a different answer, and so on. It violates one of those. So pretty much you can say that however you want to do the math or define your problem, whether it's frequentist or Bayesian, in the end, you'll either agree with the Bayesian or you'll break one of these. And that's a mathematical truism. And that I find to be, when one sees that, and these have been proved by Cox and James for more than, I think, 20 years now, that you have these differences. So there are these differences. There are, I think, still significant philosophical differences of which we don't practically possibly not care. There are definitely significant practical differences which we can see in kind of the best practices versus what's been covered, and I believe there are probably significant pedagogical differences, and those would be interesting to explore. And I'm just going to list a few here. I've gone over them in other places. You can find them on my slides, or I'll do it another time. But you can find problems in frequency statistics where it depends on what the experimenter is imagining at the time. Or you can find a 95% confidence interval that is wrong 100% on the data because it's correct for the population but not for the data itself. You have issues dealing with distributions that have no sane sampling distribution, like the Cauchy distribution. It's a great one. It has undefined moments. So like I think its variance is infinite. I think its mean is undefined. It has a median, but it's totally screwy. And so when you try to do any kind of sampling distribution type of stuff, it just totally barfs on a Cauchy distribution. Now you might wonder how often are our students really going to run into like the Cauchy distribution, right? There may be, you're grinning on this. I'm not sure if have you come across it.
Yeah, it's actually used in some value at risk modeling in finance.
And I saw a simple problem with a lighthouse, where you're getting beams of light along a beach at various locations, and you're trying to infer where the lighthouse is relative to the shore, and you end up with actually a Cauchy distribution. If you use like the mean, it's all over the place and so on. But it's perfectly well described with the probability, or in other words, the Bayesian approach. So it's like those sorts of things that come out. In fact, E.T. James, who published one of the big books on Bayesian analysis, said that he had real trouble trying to publish this result with the Cauchy distribution, showing that it breaks, because the reviewers said, everyone knows the Cauchy is a pathological example, and even though he was demonstrating that it's not pathological from the Bayesian perspective. So and he had trouble in the field trying to publish this kind of stuff, and that was some years ago, and maybe people are a bit more open on that. But I want to focus on this one more on the similarities, because I think that's where, in a sense, we can make inroads on the kind of intro stats 101 problem. And pretty much all easy, and I quote, easy frequentist problems basically read anything done in an intro stats book is equivalent mathematically as the Bayesian approach with uniform priors. So you get exactly the same numerical results. You can actually take the same homework that you've been assigning, in there. You get the same numerical answers. There is a bit of a difference in terms of vocabulary a little bit, or stress. So instead of kind of populations and samples, you often think in terms of models and parameters. And we'll see that in the example I show, or like null hypothesis rejection tests. Kind of you get a change into parameter estimation, which ends up being a bit more useful, certainly in practice. And so so this is the sort of comparison. So I just went online, grabbed, did Z test on Google, took the first one, just to kind of. So there's a million questions like this, and this has to do with cows. And I'm from Vermont, so I guess yes, it's from Vermont or Texas, right? It would be the only thing. So they have like population, and you're given some random sample, and you're told the standard deviation of the population, and so on. And they set up a null hypothesis of whether this is equal to 5 or greater than 5, and so on. Yeah, so I mean, and you can insert whatever problem you want to that has the same structure. You can t-tests or whatever. It doesn't really matter. It's just, this is to kind of show the basic structure. So how would the kind of Bayesian parallel of this look like? What you basically would say is like, okay, our model is that there's some true value and some with a normally distributed distribution, and I can get into why we use a normal distribution, but that's unimportant for this example. But and we know the sigma, and we're trying to estimate the true value mu. So we look at the probability of various values of mu, and we find that the posterior probability has a maximum at the sample mean, and has a standard deviation of the known standard deviation over the square root of n. The same problem that you get in z-test, intro stats books, same exact numbers coming in, except for here we're looking at a probability distribution over the parameter. And then we can do things like the best estimate, which would be the sample mean, plus or minus the standard deviation. We can do 95% credible intervals, and I'm calling them credible intervals because that's kind of the Bayesian version that keeps the same CI abbreviation that we assign for confidence intervals. And we can do things like hypothesis testing and actually just look at that. And we can either do this with tables or with a computer, or roughly just by looking at the standard deviations and so on. But the point here is that you do that, you get the same, this is just the rest of that example from that website, you get the same numerical answers. You get, the same times that you reject the null, the same times that you would do this, you get, it's pretty much identical, except for a somewhat of a shift in the vocabulary from kind of populations to models and the kind of distributions over parameters. And that's kind of the, somewhat shift in vocabulary, same answers, same problems, and then all the problems will look, very, very similar. And show, this is one of my favorite examples for the proportion. Yeah. This is Paul the octopus, who passed away a few years ago, I'm sad to say. But he was good at predicting World Cup matches. And so, which is good for octopus. So what they would do, was that?
For an octopus.
Yes, exactly. So what they would do is every morning they'd come down, every morning that there was a match, they would come down to feed Paul, and they'd have 2 food dishes. And they would put the flag of the opposing teams up there, and they put it forward. And whichever bowl the octopus would go to first, that's the prediction that Paul was making. All right? Pretty straightforward procedure. You got 12 out of 14 right, and just pretty good. And we can look at kind of proportions, right? This is kind of an estimating proportions. And again, so you can imagine kind of think of it like estimating a proportion. We're kind of modeling it as a coin flip with some unknown probability of heads or tails. It might be skewed heads, it might be skewed tails, and we're trying to estimate that parameter. This is the same, ends up being the same math. You can show that it's the posterior for that ends up being the beta distribution. Again, that's not critical in terms of vocabulary, but it is to get the same result. So then you do best estimates. You can get the mean, the standard deviation, and these equations will look exactly like the ones in the intro stats book. And that's kind of what I'm trying to reiterate is these look the same. And in this particular case, we end up with kind of the best estimate of 0.78, which is more than 3/4, with a relatively small uncertainty in there. And then if we look at hypothesis, is this greater than 50-50? So not a random octopus, must be psychic. Okay, and this is actually, if you Google psychic octopus, you will actually get to the page that does this. So yes, there are people who use this. And this is the same numeric as a p-value rejection. So that's what they actually do. They do a p-value rejection, and they say, oh, we reject the null, which is random, therefore it must be psychic, right? And I know statisticians realize that if you reject the null, it doesn't mean that you can just jump on any particular hypothesis you want to, but it does kind of leave it open to the possibility of someone doing this. And when I was describing this problem to one of my colleagues, he was like, I don't know why you're saying he's psychic. He's just a sports enthusiast. and so now you might notice something a little weird about the data that might make you think of other possibilities other than random and psychic. So I'm going to go back to this data, and you can kind of look to see,
I would say that the octopus likes black, red, and gold.
Okay. So although there's not black on the bottom one there, right? The yellow, right? The yellow stripe and the red stripe thing, right? It's going on. Okay, that's one possibility. Any others that are obvious? Did I happen to mention? I don't think I did. That this octopus happens to live in Germany.
Patriotic.
Yeah, patriotic, right? Yeah. So we got the German octopus and the yellow octopus and so on. And now, coming up with this problem, and this is, I think, where some frequentists get a little, kind of nervous when a Bayesian starts talking like this, because when you start talking about priors, you're like, well, how do you assign the priors? But most of the results shouldn't depend on that if you have a reasonable amount of data and so on. But even on this problem, right? Coming into this problem, your first guess was, oh, it's probably just choosing randomly, right? Before you even see the data, be like, yeah, this octopus is going to choose randomly, and then you might so that would probably be your highest prior probability, and then psychic is probably going to be pretty far down the list, right? And in fact, sports enthusiast would probably be above psychic, even though it wasn't probably on your list to begin with, but it was down there somewhere, right? But something like liking yellow or some bias because he happens to be live in Germany. I mean, it might just be not that octopus is the problem. It might be that the caretakers are like, here are the two.
Yeah.
Push forward, right? Exactly. So there might be the process might be doing that. So you come up, but those are probably less than prior to seeing the data. Those are probably lower than your assuming it's a random guess, but higher than psychic. And so you can kind of get these relative things. And the Bayesian approach allows you to go past this kind of black and white null hypothesis rejection type idea and go to actually looking at model comparisons. So we start off with psychic versus random, but we have essentially the prior probabilities here coming in, which essentially the data has to be way, way, way better for a psychic in order to offset a low initial prior probability. But we can also include more models, or there might be others, right? And this is kind of how the scientist works. You start off, you think of you have a few things, you rule out some, but then you think of 10 other reasons that it could be, and then you add that to the list. And so you immediately go from this kind of two model, or really almost one model, black and white type reasoning, and flow naturally into multiple hypothesis testing. And and that does not happen in any frequentist treatment at the intro level that I can see. And yet the math is no harder, and it's not any harder conceptually. And that I think pedagogically is a huge win. And that's how, on the practical level, this is how all these guys are doing. They have multiple hypotheses, and they're weighing the different hypotheses. The data comes in, and they adjust their strengths of knowledge on those hypotheses. They're applying probability theory, and that's one, because it's straightforward in that way. And if you do that, I think in this case I did a calculation where generously the prior for the psychic was 1 out of 100, which is really way higher, because I don't think I've ever met a psychic, and I know more than 100 people. So, but I may not have known more than 100 octopi. But still, I know a little bit about neuroscience. And so the data is good, but it's also really good for the yellow hypothesis or the German hypothesis, and that ends up putting it above random. So basically, we reject random because it's rare, but then all these other hypotheses can come in, and we can start weighing it out. And if you had another idea, then we can put it on and kind of add to the analysis, and that's the power of it. It's like it flows from this kind of black and white type of thing directly into this more nuanced multiple hypothesis testing without any real change in complexity of the problem. So I think there are some advantages to that. One, you have kind of uniform procedures that are theoretically grounded, so you're not kind of picking one one recipe over another one. You're pretty much applying the same thing. I think it's a more intuitive and flexible. It's definitely a more flexible definition of probability. The multiple hypothesis testing that comes in is a huge strength, and then it's easy to extend it with numerical methods to problems of much higher complexity. Whether you do that at the intro level or you do it later on doesn't really matter, but it naturally follows the same kind of procedures. So, why the disconnect? And so, if the Bayesian inference is so good, why isn't it covered more? And there's many reasons, and I'm sure some of you would be able to actually comment more even than I would on this. I have my own suspicions, and I'll put those out, but I'd love to hear if there are others. The history of it actually goes back, a couple hundred years, and this book is an awesome book to read if you haven't read it. It goes through the kind of history of probability theory and the kind of clash between the kind of frequentists and the Bayesians at the turn of the century, and how Bayesian inference helped in World War II in a number of places. It factored into the tobacco, the lung cancer debates, where our pal Fisher, who's like the king of all frequentist stats, was on the wrong side of that debate as a really a big smoker himself. It's always interesting when they say that there's these two things are correlated: smoking and lung cancer. And there are, they always say, like, there are three possibilities: either the smoking is causing the lung cancer, or the lung cancer is causing the smoking, or there's some third variable. And Fisher came down on the lung cancer causing smoking side, which I thought was very interesting. Essentially saying that people with lung cancer tend to self-medicate with the natural kind of narcotic effects of cigarette smoking. That was interesting.
Before they have symptoms.
yeah, there is that issue. And this is one of the reasons. This was a case where the Bayesian calculation was really showing that thing. But so kind of the history that it goes there. But I think there are. When I raise this issue, these are, I would say, the kind of four main objections that I get to the idea of introducing Bayesian approaches in the intro level. And there may be more, but these are the four that I've heard. And maybe so. One of them is mathematicians getting squeamish about subjective priors. I put subjective in quotes here. Unintuitive conditional probabilities, and the notion of conditional probabilities being an unintuitive concept. The perceived kind of advanced math, and I think part of that is because I think a lot of people who get a degree in stats or math or whatever, they first see Bayesian approaches in grad school, so they associate it with the advanced math and not with the intro algebra-based type math. And so when they think of it, they're like, oh, that's just too hard for an intro level thing. Not recognizing that if you took frequentist stats at the grad level, you'd also have all that advanced math that's obviously not covered in the Stats 101 class, textbook. So, and then of course inertia. But I have the second one I actually agree with. But the first one is and there are actually objective ways of specifying the priors in many situations. But at the intro level, all the priors are objective. They're essentially uniform. They start off with the prior knowledge. That is the equivalent. So every frequentist result in an intro stats book comes from Bayesian approach with uniform priors. Now there may be cases where the prior information is important. The frequentist stats will fail in that case, and only the Bayesian approach will actually give you something meaningful. And we saw that with the psychic example and so on. The unintuitive conditional probabilities, I actually agree with that. Yeah, I think they're unintuitive students. I think it's a useful thing for them to learn and get over. I mean, there are a lot of things in a lot of topics that we teach that we know are unintuitive for students. And when I teach physics, there's a whole handful of things, that are unintuitive to students. But we realize that we should teach these things because they're important and they have, far-reaching consequences. And I would wager that if you ask any student here, even the actuarial students, to actually define what a p-value is, you will recognize that the frequentist stats are not that much more intuitive than Bayesian. I know I also have to look up the definition of that because it's some lawyerly thing about more extreme data and everything else. And then of course the quote advanced math. It's pretty much the math set. The level of math required for an intro Bayesian class is equivalent to the same math as the other. And so I think the only other thing that I think of as inertia, that things have been done for that way for a long time. I got a question today from a colleague at Brown who teaches neuroscience, and she was asking about this, and it's related to a question Alan asked me. I think John, maybe you both asked it. Is imagine that we were to teach intro stats class, say first semester, from a Bayesian point of view, but that we don't have the ability to kind of revamp the entire curriculum. What would happen to students who then went into a frequentist, stats 2 class, right? And I think that, and again, one would have to measure this, but I think it wouldn't make any real difference in terms of the kind of impact of the performance, given that all the answers essentially are the same. There might be some interesting, we might end up finding some interesting clashes or agreement there that we haven't seen. The question my colleague asked is like, well, what if you want, she wants students to be able to read papers from frequentists in order to understand what they are. She's in neuroscience, and frequentist stats is actually very common in biology. And so in the kind of the published literature, and the way I answer is like, look, you just say it's the same thing as like the Bayesian with uniform prior, and then so you can just kind of do the mapping with the parameter estimation like I did before. But there might be other any other ideas on there that you think that might be resistance to this.
No, I think your second point really is, like, at least for teaching 201 to our students, chapter 5 and 6 is where probabilities introduced,
right.
And then that's where you really lose half the class of
right.
who just aren't particularly capable mathematically.
Yes, I agree. And so I agree that that idea of conditional probability really needs to be kind of stepped through more slowly, perhaps, than what you would normally do. And the second thing I would say is, after you cover probability, when you're doing all the hypothesis testing and even the linear regression and all this other stuff, are you doing any conditional probability after that point? Right, well, no, you don't do it because it's not part of frequentist stats. Whereas what you were doing from the Bayesian point of view, you would introduce it at the beginning, and then you'd use it, and then use it, and then use it, and use it all the way through the entire class. So they would get like a lot of repetition on this. One of the problems with the standard approaches, as I showed, is like it shows kind of conditional probability at the very beginning, and maybe a little at the end, but doesn't really use it anywhere. So the students see this as this kind of this isolated idea that's somehow related to sampling distributions, but it's never really made clear how. But the Bayesian approach is the same thing again and again and again and again. You're always looking at probability of your model given the data, probability of your parameter given the data, and so on. And you're always doing that and following the same.
I used to think there was a disconnect, but I don't think that as much anymore. And I say that because when you get into the normal distribution, all of that's just built around probability theory.
Right, of course.
So it's there, and you can't really talk about it to the students until you've talked a bit about probability. Right. And you give them a sense of probability.
Right.
And when I talk to my students and you talk about p-values,
right.
I mean, you're talking about, basically, in English, you're talking about the probability you're wrong.
Yes. Except for, that's not the definition of p-value in there, right?
But from a practical point of view, in the business world, if you're not in a theoretical world, the reality is that from a practical point of view, the p-value is the probability you're wrong.
Yes, absolutely.
How far are you sticking your neck out when you're telling your boss,
this
is going to be, the new ad campaign is going to make a difference.
And
that's what the p-value
and what you're doing is you're using the Bayesian definition
And that's why I'm just going to say, I feel like when you talk about this, these two camps,
right.
And I go back to what Thomas said before. If you look at everything just from a math perspective, I feel like somewhere someone has drawn this artificial line that says you're a frequentist or you're Bayesian.
Yeah, there's certainly shades of gray and stuff.
You know, that people who look at it just from the mathematics of it,
Uh-huh.
I always scratch my head, and I don't get the conflict.
Uh-huh.
You know, I look at it like you mentioned, if you sit back and you look at the mathematics of it, you know, it'll just, I mean, when you're talking about the normal distribution, hypothesis testing,
right.
It's all based on probability theory. It's all probability.
The typical way that it's stated, and at least in the intro stats books, and maybe you know this, you know, maybe the textbooks themselves are the problem, rather than what the instructors are thinking, right? Because the textbooks don't actually say that, what you're saying.
Oh, I know. There's some funny,
right.
You know, they try to be very rigorous.
Right.
They try to be very rigorous with it.
And then when when they do the normal distribution, they're always talking about the kind of comparison to population, right? And which in some cases it makes sense that you have a population, like I think in terms of voting. You have clearly you have a population.
In some cases you have population.
Right.
In some cases you don't.
Right.
I mean, you got two samples.
Right.
I got two marketing campaigns. I got two samples.
Right. Well, the way I think it from the science, like for instance, the mass of Saturn. I get an estimate for mass of Saturn. I have some uncertainty about that. There's no notion of population anywhere in there, and so you have to fall back on this idea of we have a population. So. If that's the case, like if you think there really is no difference, then shouldn't I see somewhere in an intro stats book probability of my model being true, or probability of a parameter in my model being some value? I mean, do you ever see, for example, do you ever see something like this? Probability of my mean value being, something is, some normal distribution. Around the sample mean and so on, and some sigma. Do you ever see that? This thing over here. You see what you see is some sort of sampling distribution of this. You'll see a distribution of X bar of the sample mean, as if it's in some kind of population or whatever. You never see that.
Well, I guess I'm kind of. What is your that? That's your.
This is a parameter in my model.
I understand that, but you've got written on the other side of that equal
yes,
sign.
my.
Isn't that your sampling distribution?
No, it's not. This is a probability distribution on my parameter. So it specifies the state of knowledge I have about this parameter. So I can plot it. For instance, if there's my mu, and it'll have some peak if it's normal, right? And the peak is at the X bar. And so my best estimate is the one with the maximum probability. Yeah. And I can talk about, I'm 95% sure that I'm in this range, right? And talk about that. And this is a probability. This is not a sampling distribution. This is not a distribution over X bar. This is a distribution on my parameter itself.
Yeah, and at the same time, when you
mathematically they're the same.
No.
Right.
I mean, also, there are some situations where, in a way, that concept does apply. I mean, like if you're doing quality control on a production line, or even if you're doing an opinion survey, and you have a suitably stratified sample to whatever. But I mean, those are situations where those assumptions do apply.
You would think so. However, I think that what the levels of uncertainties, even in like some kind of survey, go beyond the kind of sampling from a population. Otherwise, if you were to sample everyone from a population, you'd have perfect knowledge of this of the system, which you don't have if you take kind of a voting of something.
But there the problem is one of the, whether or not you really have the probability experiment that you think you have. You have about how people, if you're given a sentence, a question, a survey question, is there really, such a thing as everyone having this or that answer, yes or no. I mean, like.
So what you're saying, it depends on the population you're imagining you're comparing to.
I mean, if I'm sampling a population for, do you have 6 toes or not? I mean, like, if I'm sampling the population for an objectively verifiable property, then the assumptions are clearly fulfilled. If I have something where it depends on the tone with which the interviewer is asking the question, and then we are having a different sort of, but that's a different problem. It's not with the probability of it, it's sort of this.
Well, I mean, I would wager that the number of times you're in the former case is pretty rare, unless you're in the physical sciences, right? You know, I think the case where your uncertainties are so low that you're measuring something, you know, like really, if you were to measure every single one, you have perfect knowledge. I would say probably only happens in the physical sciences, which is one reason why, you know, when you raise this issue with physicists, they're like, you know, what are you talking about? Because their perspective is that everything is probability, and they've been doing Bayesian stuff, they just don't have a name for it. You ask an economist, the same thing, and they're like, what is this frequentist Bayesian thing? And then once you start describing it, they're like, oh yeah, we do Bayesian stuff all the time. So like sometimes like, people know that they're doing that, but the fact that you didn't know that this wasn't a sampling distribution, I think comes into this kind of communication issue between kind of Bayesians and frequentists, that there is actually a difference. And when I first learned this stuff, and believe it, actually I started first learning this stuff when I came here. I never took an intro stats class. And I was always bothered when I was reading biology texts, and they were all kind of statistical significance and stuff, and it was like not something I ever saw in physics because of just the nature of the history of it and so on. And so I started reading through intro stats books, and then like all the math made sense. And then I'd get to the chapter on the sampling distribution of the mean, and I'd be like, what are you talking about? And I had no idea. And it kept like, you know, running into this wall until I realized what was going on, and that there was this kind of imaginary population that the frequentist was always comparing to. And then I saw an example, and I give it in another talk, where depending on what the experimenter imagines the population to be, they get significance or not, given, you know, standard procedures. And that one example, which has to do with flipping a coin like 12 times and coming up like, you know, 3 heads out of 12, and asking whether this is evidence for strong evidence for an unfair coin. You know, it depends on what population you imagine it to be. If you are really thinking in terms of as a frequentist, as you know, as compared to a population, when you give the analysis from a Bayesian point of view, it doesn't depend on that, and that to me is a huge strength. That, I mean, you wouldn't see it in this, you know, the intro stats textbook, but it's that sort of thing that kind of is the background where all this is happening. Yes.
One other application where I think it's really hard for me not to understand from a frequentist point of view. That would be in finance. We talk about risk capital. We talk about how much capital do we need. We're trying to manage our risk, and we're trying to manage to, okay, well, we want to have a risk to kind of go bankrupt over 1 year horizon, no more often than 1 in 200 years. So we have sort of a clearly defined goal. There is a very, like, I mean, that means something. Okay? I mean, you literally need to put up that risk capital. I need to ask my shareholders to chip that in. Yeah. And I don't know, how do you interpret that from a basic point of view?
I think that comes into what we call decision theory, where you have some utility function across, and you have a probability distribution over the various outcomes that could happen given your model. You multiply by that in the utility and do some kind of either expected utility or min-max or something like that. So it goes, you know, one step beyond probability theory, because then you also have to attach value to the various outcomes. That's I think where the difference would come in.
And at the same time, like every insurance CEO, I'm sure all banking CEOs, they will know, my value at risk of going bankrupt is that's what how much capital you need. I don't understand that. I mean, that's
Right.
something, that's a number I can communicate.
I'm sure that number would be the same. I mean, if it were calculated in the
But
same,
I also
in the
need to
same way.
communicate, like if I'm talking to a CFO as an actuary, okay, and make a recommendation about, okay, given your risk preferences, you should put up that much
Right.
capital. I can explain that meaning, okay?
Right.
And that
It comes to a dollar amount essentially, right?
Yeah, I can tell. Yes, okay. Well, if you put up $500 million and then have that be your capital, then
Right.
your chance of going bankrupt is this. And the CEO is happy and does the thing again. The CEO is not going to.
Right. My guess is practically they'll probably come up to the same answers. But there may be cases where prior information would need to enter that sort of system. I'd be interested in going through that example with you, like just numerically to see what it would look like at some point.
The point is not about how you calculate. The point here is I sort of have a responsibility to the public, so to speak, to explain in terms that they
Right.
can stomach.
Right.
And
I don't see how that would be any different here. I don't see how that would be any different. You'd end up calculating the same dollar value with the same chance of going bankrupt and so on, as long as your model assumptions are correct. One of the things that the Bayesian approach forces you to do is basically put all your model assumptions up front, something that many times statisticians don't like to do, or they're kind of hidden in many ways. But the Bayesian perspective really forces you to put everything concretely up front.
And in fact, I think if you look at my finance colleagues here, if you look at kind of the catastrophic things that have occurred, the banks that have collapsed, the Lehmans and those kind of things, the fault in those models was a fault in priors. The presumptions of distribution were in fact wrong.
At the same time, no Bayesian analysis is going to take care of black swans either. I mean, if you didn't know about it somehow, then you put it in your model. I mean,
but that's true for anything. That's true for anything.
I know.
And ideally, models should not be sensitive to their priors. I mean, that's the and one can test for that. One can see how sensitive are these things to priors. You would always want to go back and always test. I mean, like scientists can be wrong, right? You can do an analysis and come out wrong. The whole point is, you can make concrete predictions in there. And I'll go back to the thing I started with. I mean, the fact that all these huge successes in statistical inference are all from a Bayesian point of view, to me, even if I'm not in those fields exactly, to me immediately communicates the message that these people who are doing cutting-edge stuff and are at the top, the best that we have, are all approaching it in exactly the same way. Now, that tells me something. And it may be that, mathematically ends up being identical, and that they themselves think of it as like, from this Bayesian, whatever, But even that tells you something when you look at every single intro stats book, and they're all one-sided. And they have things like, subjective probability is totally arbitrary, stuff like that, which is just ridiculous. Or they have this kind of longer, they don't even hint at what probability should be, and that they don't even mention Bayes, which is phenomenal to me. So when I see that by itself puts it in the two camps, regardless of anything I'm adding to it. Now, it's probably the case that for professionals that line is seriously blurred, but I don't think that is communicated at all to the students, or at least that one side. So I figured, hey, what would a Bayesian Stats 1 course look like? And it might look a bit different than what you would normally do. So what I did is, I broke up chapters. I copied them. I think that might be from Navidi and Monk. This is on the left-hand side is the table of contents of intro stats book. On the right-hand side would be kind of the chapter headings for what might be one way to do that. Again, what you would find in a Bayesian approach is that you would spend a lot more time on kind of probability things, kind of stretching that out, doing lots of examples, especially with conditionals and so on. Less on kind of numerical measures, although you would have that. You might break up a few other things. So, for instance, a lot of the distribution things would come into kind of model comparison and parameter estimation, and so the vocabulary is a bit different. as but this again, you can go through all the same examples, and then you can have things like hypothesis testing about means and proportions and so on that will probably be kind of merged under the kind of parameter estimation in general, and you would do a lot of the kind of best estimates and the uncertainties in the same chapter that might be broken up into separate chapters in an intro stats book. And then later chapters which would involve multiple variables, you would have other chapters that would do that. Again, a lot on models and parameters, and that's kind of the recurring vocabulary that you see in kind of the Bayesian approach. And kind of, again, I'm not my background's in science, and I don't want to stand up here and say just complain about stuff in the kind of put your money where your mouth is. I actually have a textbook that follows this same approach that I wrote, just because I felt like someone had to put something out there at least to start the conversation and to start doing that. The last 2 chapters still have to get written on the multiple variables, but you can download this book yourself for free. So the barrier is basically 0. That's a deliberate choice. Not just because I don't want to deal with publishers, but which I may eventually, but I still want to keep the kind of downloadable free stuff. I think from a marketing point of view, it seems as if an intro stats, if a professor who teaches intro stats sees a textbook, right? First of all, you want to lower the barriers for it, so making it free also helps. But the second thing is if they have the title Bayesian anywhere, or Bayesian's kind of what, they just go, oh yeah, whatever, that's one of those. They're going to put it off to the side. So I deliberately did not use that, and I simply just use probability there, and that's really what it is. So essentially, it introduces probability, goes through a lot of examples, introduces the basic rules. We use cards and things like that to get standard examples to kind of talk about probability, and we work our way up to just discrete model comparison, and then parameter estimation and model comparison in those cases. And that's kind of like my put your money where your mouth is kind of thing. So I can stand up here and complain, but I have something at least to contribute to the world on this. There's also, if you want to do things on the computer, there's also software available for the book that's also free. It uses Python, which is freely available. Again, trying to make everything as open as possible so that people can shoot it down, criticize, add to whatever you want to do, just to bring the discussion to the table. And that's my. Would
you have a separate course? I mean, are you thinking of this as a replacement?
Yes. I mean,
the only reason I ask that, I'm thinking of some of the basic topics that students don't have a grasp of. Okay?
Right.
Like the differentiating between a qualitative and a quantitative variable.
Right.
All right? Frequency distributions. Cumulative frequency. Just basic, basic things.
Yeah, there's a kind of numerical.
What's the 75th percentile mean?
Right.
Things that a lot of students in the classes don't have a grasp of.
Absolutely.
So where is that? When do they learn that stuff? The stuff that when they go and they sit in their cubicle in their office and their boss says, oh, can you get me the median of this?
Right. So it actually occurs in a couple of different places. And one can argue about the kind of the ordering. And this is one possible ordering.
I'm wondering though where they learn.
So what I did, and a lot of that comes in somewhat later, but comes in both kind of when you do parameter estimation. A lot of times you look at you'll have once you find the posterior distribution, you have kind of best estimate. Then you get things like, especially when you actually do proportions before I do the normal distribution. So in proportions, you have a skewed distribution, so with low data. So your mean and median are not the same. And so then you can talk about why would you want to choose one over the other and so on. So that comes into the
distribution.
Yeah, exactly.
Things like
right.
that.
Right, exactly. And that would come in.
A lot of variation means you can't get as good estimates out of it.
Absolutely, and that would come in.
Where is that?
And again, it would be a lot of it's in right here because most of the up until this point, this is mostly discrete models, and then it moves into continuous when you do parameter estimation. So the continuous stuff is afterward. So we start off with kind of intro probability, then you do kind of discrete model type comparison, then kind of like things like, you know, positive, negative tests for diseases and things like that, and do the psychic octopus in that case, and any of the other things. And then you move into continuous from the coin flip example is actually where I move it from discrete to continuous. There, at that point, then you can, and even before that, you can talk about medians and means and so on. But I think mostly I do that in the continuous case. But I do that at the same time as I have best estimate and uncertainty, you know, in the same place. And so you always have kind of best estimate and uncertainty, and then you have like the quantiles and the percentiles and so on, and it just comes naturally out of any. Once you have the posterior distribution, this is all the information you have. Everything else is just, you know, how do you deal with these distributions? You know, peaks, widths, that kind of thing. And you know, maybe you'll have something that has 2 peaks in it. It's like, what do you do with that? The mean is terrible, right? The median is probably terrible, and so you have to look at the distribution. So then, I'm not sure if I come up when I do an example with 2. Yeah, I don't think I do an example with 2 peaks in the posterior, but that certainly is you know, a possible thing that can happen.
I don't know if Mike meant just basic descriptive statistics or
Yeah,
data analysis.
Yeah.
Just basic, you know, just the real, like, you're given a data set, just describe the data set. Just the real basic, which is usually the first, usually the second chapter of a
Right. Well, see, that's different, and I'm not saying that's not important, but the order is different. Okay, so it actually ends up being somewhat later when we apply the probability analysis to data. That's why it appears later. In a frequentist perspective, everything's a sampling distribution, so you're always counting. And so you want, you know, you start off with data, right? You're basically, even your population in a sense is data, right? You know, and so that's where it's important. But for the Bayesian, everything is probability, so that's where that's important. So that's why that stuff happens earlier rather than later.
You know, I'm just thinking that, like, I feel like a lot of times coming out of the classes, some of the things that are most important for many of the students are that when they get out into the world and are working,
right,
they're going to have reports flying across their desk with tables of numbers and whatnot. And they're going to have to be able to look at those numbers and interpret those numbers and use those numbers to make decisions.
Absolutely.
They're not, you know, they don't even, you know, they may not have to think of it probabilistically. They may just have to interpret, you know, what did I just get?
I would actually disagree with you there. I think every decision is probabilistic,
Well,
whether you admit it or not.
Maybe I'm not using the right terminology.
But I
just
think
like I don't describe the p-value like the frequentist describe the p-value.
I've taken a couple classes with Brian, and we can use probability for like literally anything. I took like what was the first? Oh, I took physics, and then I took statistical modeling, and then I took a brain science class. And so across like all the different topics, he might have us read like, okay, read chapter 2 before class, and like just reading through the book, he didn't even need to go through it that much in class. It was easy enough to follow. And then we use probability for literally any example you can think of, and even every decision, like in the brain science class, every decision that you make is kind of based on probability.
And
I would argue, though, that you don't represent 50% of the students in my Stat 1 class.
Look,
I mean, clearly you're into this. You're sitting here, just like the rest of us.
But I thought I was really terrible at math, and then like looking at from this perspective, at least I was a science student, so at least for science, I found Bayesian to be much more comprehensible.
And the other thing, I mean, for instance, I taught the physics lab this semester, right? You know, and there everything was that you have you know, measurements, we want to, you know, estimate quantities and so on, and I kept drilling into them like, look, you know, no estimate is useful unless you have the uncertainty, right? You know, because the difference is like if I said I know the distance from here to my car to within a millimeter, that's pretty cool. But if I said I know the distance from here, my car that's parked in the parking lot to within a mile, you'd be like, you don't know anything, right? You know, and the difference between being really cool and not knowing anything is, you know, I might have the same estimate, and so, you know, everything. But also the way I see it is, it's not like just the person who's like, you know, in their cubicle getting numbers thrown. It's anyone, coming out, picking up a newspaper or checking Google News or whatever. Latest medical study says that the carrot that you ate today makes you less likely to develop lung cancer later on. Right? And to be able to reasonably say what are they really saying and not. It's not just for the person, the practitioner. It's really for everyone. I mean, coming in any kind of claim is really the probabilistic, and so that's the way I see it. And yes,
I kind of agree with everything you just said. However, it sounds like you're throwing the baby out with the bathwater. That's my problem with it, because there's a lot of valuable information that students get just from basic thinking about that there's a difference between looking at data when I'm talking about somebody having blue and brown eyes versus a measurement. So that's just a difference that many students don't grasp right away.
And there is this, you have to be able to describe data in order to describe a model, and formulating proper models, right? Is I think look at this like an octopus, right? I mean, that's immediately. After you rule out random, essentially, immediately it brings in this flood of like, okay, how do they actually do this thing? What do we actually know about the process?
Question?
What?
Can you email us a link for your book?
Yes, it's yes, sure.
Okay, we have another meeting now, but that's.
Yep.
Thank
But
you very much.
if you search for
your
Brian
research.
Blaze on Google, first link, or see I'm feeling lucky, will bring you to my website. The talk slides are there, and the book is there as well.
All right. Thanks, Brian.
But I'll send you a link as well. And so was it saying? Oh yeah, so immediately brings in that, and yes, I agree with you. I mean, there's a certain amount of kind of data science that may require a dedicated chapter, right? Just in terms of dealing with data and things like that. And I don't have a problem with that. And I don't think that's necessarily like frequentist versus Bayesian. It's really on the inference side that you have the difference. And I don't see a problem with that.
Okay.
I mean, I may not have focused as much in my book so far. I mean, it really is a work in progress, and I'd love more examples, and I'd love to have to see things from different perspectives and so on to pull in. But that was because I was focusing on other things that I knew were not covered. I wasn't sure.
I guess where I'm coming from is when this seems to me totally appropriate for a second level course.
I think it's totally appropriate for all levels.
Well, all I'm saying is
I
I feel like that you can't leave out a lot of that information that has to do with dealing with data.
Mm-hmm. I wouldn't suggest.
And if you're talking about a year-long course, that's fine. I just don't think you're going to be able to get it all in one semester.
That's possible, and these I think are more strategic than anything else.
Too.
But the way I would see that though is then the proper approach, whatever that happens to be, should be Bayesian at its core. Whether you focus first on all the data stuff and do only a little inference, or you do kind of more inference and a little less data in one semester, or you plan for everyone taking a full year. However you want to strategize it, I think the core should be Bayesian. And I think it's and I've been able to cover enough probability to be useful in a class that's not a math class. So like in physics, for example, I spend maybe a week or so, maybe two, on probability, going through pretty much every example that we have in there. We apply it to physics examples and so on. But the thing is, it's not something that you would, it doesn't have to be just like in a math lesson. And I don't think I'm quite so pessimistic, but that's an empirical claim I think one could look at.
About that, I think if you're talking to a physics class, you're talking about people who probably don't have a big problem solving a quadratic equation.
No, actually, I'm not. I'm not. I can tell you for certain that that's not the case. I mean, you always have a spread, right? There's a distribution, if you will, right, of abilities. And it's I wouldn't even say the average is strongly mathematical. I just don't, not from my experience anyway.
I do have a different question about, like, given where we are at right now, and
Right.
for example, we just went through a departmental review with the American Statistical Association, and basically a pretty clear, we got our marching orders of what we have to cover in our into the stats class.
Yes.
So it is,
That is
given that we have those marching orders,
Right.
is there sort of a laundry list of things, like even just a one-page handout, you would have things you would like us to teach to our students about, they're going to be learning frequentist hypothesis testing. It's not going to be, I can't change that. However,
I'm not sure. Okay, I see what you're saying.
Or I've been told to teach my student frequentist hypothesis testing. Okay, as I said simply, I have the memo from Chris Kennedy.
Yes.
So
that's fine.
So what should I teach? At least my more able students. What should
That is a very good question. And it's something where it's like, what's the best compromise in this? And I find that one of the reasons why I kind of bring this up is that by highlighting the similarities, it allows you, in a sense, to. Someone said this was subversive. I think it was Alan Downey who said this approach was subversive. A pure Bayesian would be like, yeah, just chuck out everything and blah, 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 right? But here's kind of subversive, basically saying we're just going to use all the Bayesian vocabulary, do all the same problems that we would do as a frequentist, get the same answers, and then and so by kind of being subversive, doing the same things that you're supposed to do in an intro stats class. But the stress and the vocabulary might be a little bit different, and then maybe at the end you can kind of talk about maybe the how you would map on that vocabulary if you happen to see it either going into another frequentist class or going into somewhere else. But by laying the groundwork in the kind of Bayesian vocabulary, you kind of undermine the overall hold that frequentist seems to have on the undergraduate pedagogy. And hopefully convince people that this is actually a better approach, and probably push the mountain a little bit. Now, I could be wrong on that, and that's fine. I mean, I'd like show me I'm wrong on it. That's how I would see it. It's basically to be subversive, because because the second I find frequentist descriptions. Either if they're identical to the Bayesian one, I just don't like the vocabulary. It's like the idea of populations just doesn't make any sense to me. I hear I'm like and so once you do that, then to me you're basically talking probability theory and you're basically being a closet Bayesian anyway. I'm just saying come out of the closet. And if you don't really care about the definition of p-value, then use the Bayesian one, and at least know that you have a good theoretical foundation.
Know we're in a closet. That's the
Well, no, but it's I can't teach what I'm teaching right now without talking about sampling distributions. I mean, there's just no way I can. It doesn't work.
It would be really interesting. You and I should need to talk about this and go through. I would say some specific cases where you feel that you cannot get away from the frequentist stuff. Oh, you're very welcome.
Well, I mean, this is, for example, to explain what a p-value is. What a
p-value is the probability that your hypothesis is true. Or, as Mike says, it's the probability that you're wrong, right? So whatever one you want to take the 95 to the 5, whatever, I don't care. And so
it's a conditional probability conditioned on the null hypothesis, and so in that sense,
that's not the technical definition. The technical definition involves it's the probability of more extreme data being observed in the population that you happen to have. It is not phrased as a conditional probability. If it were, I wouldn't have a problem.
But okay, I mean, I would say more than that's the only way I can make sense of it. I admit is okay. I'm viewing it as a conditional probability based on let's assume the null hypothesis is true. And then that's what the probability would be. I mean,
you're speaking the Bayesian language, essentially.
I am, in the sense that it's the same time. It's the same time to make sense of the whole setup. And
at what point in what you just said did you use the word sampling?
because I'm deriving a sampling distribution
No.
based on...
No. But when you described what a p-value was and everything else, I happened to notice that you didn't use the word sampling at all in your explanation.
Well, I did in the sense that, what I'm calculating, the way I'm calculating the probability is I'm calculating a sample distribution
Okay, well, how about
conditional on the null hypothesis being true.
Why can't we just simply change that name and say you're calculating out the posterior probability of your particular parameter, and then you just look at the probability of it being greater than 0 or whatever, in that way. Calculate that. It's a conditional probability on the data that your parameter is greater than 0. It's all the same vocabulary that you just used, and I don't even need to bring in a sampling distribution.
Well, that's where I'm not quite connecting, because it's simply, okay, ultimately I am talking about the sampling distribution.
This is not a sampling distribution.
I know that this is not a sampling distribution.
But would you agree that from this, I can calculate out the probability that, say, mu is greater than 0? From this distribution. Normal, it's the normal distribution, I probably have to put that over sort of then here just to make it the parallel to the other one, right? From this distribution, I could calculate out, from this, the probability that this parameter is greater than 0, right? Would you agree mathematically that's correct?
Yeah.
Would it be numerically identical to a p-value? Or 1 minus it? John's saying yes.
And at the same time, I have the problem connecting that to the way I'm setting it up, how I'm explaining what is going on, how I'm explaining. We spent 2 chapters on basically explaining, okay, what is X bar viewed as a random variable.
Well, you wouldn't even have that.
Well, yeah.
I don't even use the term random variable anywhere in my book. Because the randomness, the probability part, is a measure of your state of knowledge, and so it has nothing to do with the actual, thing in
random variable is a mathematical.
Sure. But you don't. The thing is, you don't need the idea of a random variable in order to talk about these things, and I think it's introducing a concept that is both challenging for students and for me doesn't make any sense. When you talk about X bar being this random variable, you're immediately talking about a population. And to me, population doesn't make any sense. Because the example I always think of is mass of Saturn. What the hell's a population for that?
Yeah, okay, but you talk, and we're not arguing about that. They're simply arguing about what is it I'm teaching my students. And when I'm teaching my students, I'm definitely talking about sampling a population to find out what is the mean height of men in that population.
Right. Sure. The thing is, all I'm saying is you change the vocabulary a little bit. You get the same answers, and from the way that you're talking, you are personally thinking about it differently than what you're teaching your students. Unless maybe you're not, maybe I'm not, or at least when you say something, I'm probably reading it differently. And I don't think in terms of sampling distributions, but I can totally understand what you're saying, right up into the point where you say, and I have to introduce sampling distributions, and I'm like, no, actually you don't. And then so we agree all the way up to that point, even on the answers, even on the mathematical form of those answers. Even not just numerically, but just on the analytical form of those answers. And we agree all the way up. Until you get to talk about sample.
What's the fundamental difference is that in the end, you interpret your statement as saying, okay, there's a probability distribution for the true parameter being is distributed that way,
right?
And as I would simply have to say, well, no, I can tell you anything about the true parameter. All I can tell you is that if I assume that is my null hypothesis, then the probability of getting this outcome is pretty small. So I better reject my null hypothesis. I can't make a statement about the true this interval. You can call it a confidence interval and say, there's some chance it's in that interval.
Right.
but this may or may not be true.
And yet you say that you agree with probability theory. And what is probability theory other than assigning states of knowledge to various claims, to various truth claims, right? So if you accept probability theory, then you are actually saying that you are assigning some confidence or some degree of belief to various, quantities, including a possible true one. Now, you're never going to know what the truth is. Like, you're not going to, there's no golden tablet that's going to be, handed to you, right? But you can specify your state of knowledge, given that, and you can use data to constrain, the parameters in a model, and you can, talk in all these ways, and at no point. At least I don't get the sense that I need to bring in the idea of a sampling distribution at any point in all of that. If I just stick with probability theory, the sampling distribution stuff just becomes irrelevant. And then you're always talking about posteriors on the parameters. You're always talking about your assessment of your knowledge given your data. It's always conditional on the on the data. Steve, you've been very quiet on that. don't want to jump into the fray here.
No, it's I at least relative to this particular topic, the more complicated mechanics are what is most useful for me. So the idea of going and trying to conduct inference where I don't have a predefined distribution going into the thing is. And those sorts of methodologies, at least from what were presented at UConn, don't necessarily fall into Bayesian or Frequentist. It's more about like, well, let's go with whatever tool happens to be the best way to answer the problem, or given the data that we have.
Sure, but the thing is, I think again, if it's a statistical inference thing, then you're following probability theory most likely, yes.
Yeah.
Then that's all Bayesian is that. Do you phrase things a lot in terms of sampling distributions?
Well, it's hard to talk about like that because if
it may depend on the problem. But
the way that we do publications is actually so much looser than kind of the way that we're discussing things right now.
Right.
Right. If I present a table with t-stats. Nobody really cares like how I arrived at them or how I arrived at the hypothesis or anything.
Exactly.
Because that's the only thing they're looking at.
Right. Yeah. Fine. Yeah. And so the final answers of do you reject the this hypothesis or that or so on, all those will be the same across frequentist and Bayesian. There's no advantage there either way, right? Regardless of it. And so people will use whatever is in their experience and so on. My claim is that, if we know that the Bayesian approach can be, like the example I gave with the cyclic octopus, where we went from essentially this idea of kind of, this is one of the things I dislike about kind of p-value rejection, null hypothesis rejection. I think it's not at all the way a scientist works. You never put something up as an explanation and simply shoot it down without alternatives. And that's just not ever anything a scientist would do. You always have more than one hypothesis, and that's never communicated ever in an intro stats book. And yet it naturally flows from probability, very straightforwardly. Like you can start with the kind of two-value kind of like, yeah, it's greater than this or that or whatever, and then naturally go immediately the next sentence into multiple hypotheses without missing a beat. And I don't think that the frequentist approach has that flexibility. And that's where I'm like, it's like we have a methodology that we know is theoretically sound, does not have any pathological examples. I could show some, pathological examples with the frequentist approach. Gets all the same answers that you would get in an intro stats book, and yet is far more flexible in dealing with kind of just the next level of complexity, and is empirically better because you can just show that the best inference that's being done in the field is essentially all Bayesian, or as I say, kind of closet Bayesians. And essentially, they're kind of doing things, phrasing things in terms of frequentists occasionally, but when it really comes to it, they're like, yeah, really the p-value is the probability of the null, or it's like, okay, well, sure, but
I would say that the most useful thing that you could probably get out of this as an undergrad is not so much kind of the vocabulary, because, and we're still doing the same side of the calculations.
Right.
But the understanding that the experimental results will change depending upon how you frame it, and I think that becomes much more kind of plain to see in the Bayesian
Yes,
context.
that is true. We have to put all the models up front,
Yeah.
and all your assumptions are like right there. And because I think it's more hidden, I think, in Frequentist.
So the big great example is when you're talking about VAR calculations. Right after the financial crisis, if you look at the rise in the use of conditional VAR, I mean, all of a sudden everybody was like, oh yeah, we all have a conditional VAR model too, but nobody used to look at it, because the conditional VAR model always resulted in you having to post more capital. And so everybody would come up with fantastic reasons on why that wasn't accurate, and we could just assume some sort of stable distribution because we had this sample and we only looked at the past like 60 days, and hey, there's no financial crisis in the last 2 months, so therefore, our value at risk was really tiny and we're awesome.
Yeah. So kind of sweeping stuff under the rug.
Yeah. And I think if we kind of got used to, I mean, that was, everybody kind of knew it was BS, but the intuition that just how much BS was there is not made plain until you start thinking about exactly what sort of assumptions are going into that model calculation. And
have more than one model on the table. It's like, you can't even do model comparison without more than one. And so that's, and usually you have more than one. And that's the thing that's interesting.
So what do you think is the chances of, let's say, do an elective 201 Bayesian, 201B class that students will get credit for to meet the requirement? But I mean,
we've talked about
you talked about this, and it's whether, and part of this is, and there's bureaucratic issues about, like, how do you do cross, team teaching, and I'm not in the math department, so how does that work? And so there's those sorts of issues. That's just kind of mechanical. But what would be awesome to do, because I think one can start to address some of these concerns by doing exactly that. But then roll in essentially some kind of pre and post assessment on both the 201A sections and the 201B sections. And see that, and I'd also propose a follow-up measure in the the 301 class, which will probably be Frequentist, and compare the 201B, 201A students in the 301 class. And those aren't literal numbers, but to see how they do in the next class, right? 350. So and that would also be an interesting thing. I don't claim to know the answer to that. My guess is it wouldn't have. I don't think it would have a measurable negative effect. That's a guess. I could be totally wrong there.
You have a huge selection effect, though.
But you don't have to.
Yeah. It depends. Well, it depends on how you do. I mean, on how you set it up. You have to do random or whatever. I mean, you have to do some way to.
You don't have to
deal
do
with
it though. Over the summer, you have the students, especially now they're taking 201 in the spring. They have the summer. They tend to forget.
Yeah, exactly. So it has that anyway. So.
Yeah, so it's almost like
Right.
slate, but tabula rasa, but
Right.
it's like.
Right.
Yeah, no, I'm just
But it's
saying,
a good question.
I think to answer, I mean, some of these are sort of pedagogical questions. I don't really know.
I don't know.
What if you present students with that material in that order? What percentage of students is going to be able to go with that? Because, I mean, quite frankly, I mean, I do find it appealing. I'm just also faced with, okay, what is the practice?
Right. No, I'm fully on board with that. I mean, and I don't know the answer either. And it's I think using students as just guinea pigs, but that's pretty much what you have to do.
No, that's why I'm saying. I mean, you can't do a controlled study in that sense. I think.
Well, you could, but maybe not practically.
Yeah. I mean, like to start gathering some experience.
Yes.
I would start with an elective class, and then maybe to the advantage of the students, maybe they could
take either one.
And then that way you can sort of iron out the kinks and really figure out what students are really learning. And then you could go to a more large-scale clinical trial to...
And you're right, absolutely. I mean, I put the book out there so that, it's something kind of puts a stake in the ground. And it's like, this is one possible way to do it. There might be others, there are probably better ways to do it. It's just one way to think through it. I think that there are advantages to it. And I've used the book in my classes. When I talk about probability theory, when I talk about inference, I've used it in various things. I'm going to actually add a chapter for the physics lab just so that they talk about uncertainty in measurement and things like that. And so it's kind of in that sense it's kind of a moving target. But I've adjusted things based on my feedback again anecdotally. But it would be good to kind of do this and maybe get Bob Shea on on this to kind of set up how would you measure the impact and so on.
Do you have any automatically graded homework problems yet?
No, I don't have the automatic graded homework. But the thing is, all the homeworks that you normally have, other than small tweaks in vocabulary, you can still use. That's the kind of that's the whole point. Is that all the standards, Z-test, T-test, F-test, all those kind of hypothesis testing, all of that stuff. Even the mean, median, all the data stuff. I mean, all of it you can still use. It's just you have small tweaks to the vocabulary, and then you keep repeating the kind of essentially Bayesian inference plus area probability, throughout the whole thing, and you have it. So if you happen to have automatic graded homeworks, then yes, I have automatic graded homeworks now. It's just some small tweaks to the thing. I mean, instead of saying that the population standard deviation is this, you'd say that for some other either through the population or through some other measure, the standard deviation, or again, small changes that I don't think would make huge differences. But you wouldn't talk about sampling distributions, and there would be some problems where if you're probing specific things that are frequentist, then you'd have issues. But for the most part, the same problems, same answers, same thing across the board.
It's funny.
Well, I think you're downplaying one aspect that's really important for me as an actuary, dealing with relatively small data sets, trying to make predictions. Which effectively is a data set I'm selecting there that is taking a sample, and there is uncertainty imposed. Both uncertainty and correlations among parameters that are imposed by a specific model structure I'm selecting, and it is important for me to both understand and quantify that uncertainty.
Absolutely.
And so in that sense, it is for me it is important to talk about the sampling distribution, because that's exactly what I'm doing. I'm taking a sample.
No, yes and no. Yes, you're measuring something. That's
thousands of actuaries are taking these triangles all over the country and are fitting a model to it.
Right. Yeah. Sure. That's fine.
And that's a fact. That's what's happening.
Sure.
What the investor wants to know. Well, okay, you actuaries, you can do that. But sort of, hey, how likely would it be right this your best estimate or not?
Exactly, and I don't see that problem is immediately applicable from the Bayesian point of view, and I would wager you either get the same answer that I would get if we both did the same thing, or my answer would be better. Because from what I showed before, that either this is just from the I go back to way back here, that any process of inference either agrees with the Bayesian approach or violates one of those. And there are ones that I can show you chi-squared goodness of fit tests that depend on how you just remap the data. I can show you things that where the significance, the p-value significance depends on what the experimenter was just simply thinking at the time. Same data, same experiment, just whatever you happen to be imagining at the time. The frequentist p-value changes significance based on that, because it depends on what population you happen to imagine you are drawing from. And if you imagine a different population, you are actually you get a different significance value. And so it's really testing to see whether your data is consistent with data that didn't actually get observed, and you're using that to get it rejected and so on.
Yeah, I'm glad you went back to that slide, because when I saw that, I thought, I hope you're going in the direction where you take point by point, it's either Bayesian or this is wrong. And then you've made that.
Other people have done this. They're like E.T. James actually has some papers on that. Right. E.T. James has a good paper on that, and like Lindley has some other ones and so on. And there are other examples in there where they say, I think there's a 1976 paper by James that goes through like 4 easy examples where like the standard frequentist approach just gives you stuff that you can demonstrate is just wrong. And that the Bayesian doesn't have a problem. And you can push it. Basically, it happens usually in low n, where you're concerned. It happens in weird distributions that you don't often come across, like the Cauchy distribution. Anything involving the Cauchy distribution, every frequentist test breaks. Every single one of them. And so, I mean, that by itself, that one example, the fact that every frequentist test breaks with the Cauchy distribution, and the Bayesian analysis doesn't have any problem with it other than the practicality of not being able to do an integral, like analytically. That's the Cauchy distribution, you can't do that integral. So, but other than that, it's not pathological. To me, if I were doing things in a certain way, and you can demonstrate on a simple one, all it takes is one simple case where the method I was using just fails outright, and the other method, which gives me all the same answers that I've been getting, works, I would ditch that first one in a heartbeat, just in a second, and because it's like, why would you not otherwise? You end up fooling yourself. Unless there's some practical gain, like somebody's an approximate value or something, and then you do that. But then,
I think maybe one of the things that we kind of approach this stuff differently is that in finance, more data is always just used. If you can possibly get your hands on more data, it's just awesome.
Right.
But from an actuarial perspective, it's very, a good portion of your job is trying to select what data do I use.
Right.
And from that, I think it becomes very kind of fundamental to understand sampling distributions.
Sure, right. And the thing is, if you actually are talking about frequencies, and you can actually talk about the probabilities of various frequencies or so on, you can still talk about all that stuff from a Bayesian point of view, if in fact you are dealing with a sample from a known population. It's just that most of the time, in most fields, you don't end up doing that, even though the frequentist approach claims that you should. And in fact, Fisher worked in, I think, genetics. And there was another case where he was really dealing with the population, because he was given like basically ecology and so most of his cases he had basically no prior information, and he was dealing with a sampling from some known population, and he was getting these results that were all frequentists. It's just when you apply that, and you can do that from a Bayesian point of view, and that's no problem. You're just applying probability theory. It's just that is what is of very limited use anywhere else. So most of the time in science, that's not your issue. Your uncertainties can be high, whatever, and there are many fields where you have low end. I mean, I'm not a big data guy. I'm really a low data guy. I mean, published paper with 12 data points on it. It's like that's when. But the 12 data points took like 2 to 3 years to get. So that's so that's a case, and so I think that's where some of it comes from, and the history of it is done in that book, The Theory That Would Not Die, and it talks a little bit about kind of the whole Fisher thing and so on, and I think the influence of him kind of in terms of that inertia can't be done, maybe not. But I think it's just the idea of sampling distributions is just not nearly as universal as introstat books would like you to believe, and I know in the sciences they're almost entirely irrelevant. Thank you very much for coming and putting up with my rant for a long an hour and a half. So I'm going to actually stop this so that way